Okay, hello everybody. So today we are going to go over some two variable linear equation practice problems. There aren't very many, but we're just going to go over a few, and then you'll have an opportunity to go ahead and work on your independent practice, which will be due at 11:59 tonight. Okay. So let's go ahead and jump right in. Let me just make sure I have everybody marked that's here. Okay, perfect. Any questions before I begin today? Questions, concerns?
No, ma'am.
No? Okay. Okay, so two variable linear inequalities. So basically we learned that we use linear inequalities whenever we're trying to find when a certain equation will be greater than a certain value, less than a certain value, less than or greater than a certain value, or greater than or equal to a certain value. Just depends on what we're looking for. But basically, we would create an equation that contains an inequality. For example, I could create the equation 2x is greater than or equal to 3. Something like that. So basically, it's using this inequality instead of an equal sign. Okay. So here's the first question we might encounter. This one says, which notion best represents the phrase no more than 200? So we're looking for which of these notions best represents no more than 200. Well, the easiest way to answer this problem is actually to use this chart that you see here. And this chart just represents a lot of the different types of terms that you'll get whenever it comes to using these inequalities. For example, we might use this symbol to represent less than or fewer than. This would be less than or equal to. So less than or equal to could also mean no more than, does not exceed, or at most. The greater than symbol would be greater than, more than, exceeds. Greater than or equal to could be at least or no less than. So these are the different terms that we might see whenever we're being asked to use these symbols or represent these symbols. So here, what we actually see is the term no more than. And what we'll notice is that no more than is actually contained in this chart right here. And so therefore, we would look for that symbol, which is right here. And so B would be our answer. You could either use that chart, or the logic basically is it can be any number as long as it's not more than 200. So any number that's not more than 200 would mean that 200 is the maximum amount. It can be exactly 200, but it can't be more than 200. So that's why we use this symbol, which represents less than or equal to that. Okay. Any questions about this? Okay. So here is another type of problem we might encounter. And this one says, which phrase includes being equal to 50? So it must also include being equal to 50, which is represented like this. So it might include other things as well, but it has to at least include being equal to 50. And what we'll notice is things that can include being equal to are the sign equal to, less than or equal to, or greater than or equal to, right? Even these include that equal to. So we want to see which of these phrases includes that. 1 second. Okay. This first one says A is at most 50 degrees. So at most, let's say X is at most 50 degrees. At most means that X can be less than or equal to 50 degrees. So at most means 50 is the maximum. It can be exactly 50 or it can be less than 50. Fewer than 50, on the other hand, is basically X is less than 50. It has to be fewer than, cannot be equal to, it has to be less than 50. Exceeds 50 means that X has to be greater than 50. It has to be greater than 50 because if it's going to exceed 50, it has to be greater than that, cannot include 50. And then below 50 would just again has to be less than 50. And so what we'll notice after we write down all of those is that only A includes that equal to as well. So basically it's saying at most 50, which is 50 is the greatest amount. It can be exactly 50, but it can't be greater than that. And so A would be our answer. Okay. Any questions about this problem? Questions for this? No? One second. All right. Okay, so here's the next problem. And in this problem, we're actually going to go ahead and create a two-variable inequality. So let's look at the word problem. This one says, a grocery store sells almonds for $7 a pound and peanuts for $5 a pound. Let X represent the number of almonds and Y represent the number of peanuts. Which inequality can be used to find how many of each nut can be bought without spending more than $10? So we want to not spend more than $10. So our question is, which inequality can be used to find how many of each type of nut can be bought without spending no more than $10? Okay. Well, let's go ahead and represent almonds and peanuts. Well, here we're told that almonds sell for $7 a pound. So $7. And we know that X represents the number of almonds because it tells us so right here. X represents almonds. Peanuts, on the other hand, is represented by Y. And that is $5 a pound. So 5Y. Okay? And so what we're looking for is which inequality can be used to find how many of each type of nut can be bought without spending no more than $10. Well, we want to look at this term more than, no more than. Which inequality can be used to find how much of each type of nut can be bought without spending more than $50. So that means we cannot exceed $10. We cannot exceed $10. And so because we cannot exceed $10, it can be less than or equal to $10. It can be $10, but we cannot exceed $10. And so how do we represent us buying those nuts? Well, we would do 7X plus 5Y, and then include that on the opposite side of our inequality. So basically, whatever we actually spend on the almonds and the peanuts must be less than or equal to our $10, because we can spend no more than $10. And so now we just look for this inequality or answer choices. We'll notice that we can't use this one. We'll notice that this is the inequality we just created. This one we can't use because 7 is with X, not with Y. But this one we can't use because 5 is with Y, not X. And we can't use this one because we don't have greater than or equal to. So this is us creating an actual inequality to solve this problem. Okay. Any questions about this? Okay. Here's another problem we might encounter. And this one just asks, which inequality has a solid boundary line when graphed? Well, we looked at when we use a solid line and when we use a dashed line. We use a solid line whenever we have less than or equal to or greater than or equal to. And we use a dashed line whenever we have less than or greater than. And so whenever we use a solid line, we have to have these symbols represented that also include or equal to. And what we'll notice is there is only one option that contains that symbol right there. And so therefore, that would be our answer. So that means when we graph this, we would use a solid line instead of a dashed line. Okay. Any questions about this? Okay. And then here is the last problem we're going to encounter. This problem is a little bit more lengthy, but this will help us understand how we can actually go about graphing these different inequalities. So this one asks, which inequality is graphed below? Okay, so we have an inequality that's graphed here. And what we'll notice is that this inequality contains a dashed line. And so that means that we have to have the symbols that look like this. We can't have or equal to. What we'll actually notice, however, is that each of the symbols do not contain or equal to, and so therefore we can just eliminate an answer based off that. Okay, so what we want to do is find out which inequality is graphed here. We can solve this problem two ways. The first thing is we can actually go ahead and graph each of these inequalities and see if it matches or if it doesn't. Or what we can do is we can test a point within the bounds of this inequality, so within the shaded area, and see if it is true. And if it is true, then we know that that inequality is in fact the inequality we need. So I'll show you the first option really quick. I'm just going to show you how you could graph it if you wanted to. And then we'll come back and look at how we could actually just plug in a solution set, see if it's true. If it's true, then we would use that one. So give me 1 second. I'm share my other screen and I'll show you how. I'm just going to graph one inequality so you could see how you could do this. You could also do this on an actual calculator, not just one that's available online. But I'm not 100% sure you guys have graphing calculators at home. So that's why I also want to show you the other option. All right, so basically this is what your graphing calculator might look like. And what you could basically do is, if you didn't know, what you can actually do is plug in an inequality into this type of graphing calculator. So I'll do 3x plus 2y is less than 6. And so what you'll see there is you actually get a graph, and what you'll see is you actually have a dashed line, right? Because we have this symbol right here. And you have your inequality shaded. And what you'll notice is that this inequality doesn't actually match the inequality that we're given in the problem, so we would do it with that answer. And so you would test out each of these, and you'd be able to see, okay, which inequality matches my answer. So that's one way about solving this. Okay, and I'll put this in the classwork tab in case you want to use it that way. But there's actually another way to go about solving this problem. So let me go ahead and share my screen. Okay. And again, this might be a little bit more lengthy, but it is in fact a way that you can solve this problem. So basically what you want to do is you want to try a solution set in the shaded area. So basically I want to pick a point that is in the shaded area. And I will pick this point right here. So this is 3 and -2. So I'll pick that point. And basically what I'm going to do is I'm going to plug in this x and this y into these equations and see if I in fact get a true statement, right? So for reference, I would plug in 3 here, 3 here, 3 here, 3 here, because that's my x. Then I would plug in -2 here, -2 here, -2 here, and here, because that's my y. And then I would solve. And when I solve, this is what I get. I get 5 is less than -6. 5 is greater than -6. 3 is greater than 6. Oh, 13. 13 is greater than 6. And 13 is less than 6. And so what I'm looking for is which of these statements is true. Well, it's not true that -6 is greater than 5. It is true that 5 is greater than -6. It is true that 13 is greater than -6, but it's not true that 13 is less than 6. So that means we could do away with these two answer choices. Okay? Well, what it looks like is I still have two answer choices. And so in order to eliminate an answer choice, what I must do is I must try a solution set outside of the shaded area. So for example, I might try this one right here, 0 and 4. And what I'm looking for is any of these statements true with my solution set outside of the shaded area? And if it is true, then that's not the solution set I'm looking for, because the set that I need, or the inequality that I need, needs to be within the bounds of that shaded area. So if it's true for a solution set that's outside the shaded area, well, then that's obviously not my inequality, because it has to be within my shaded area. So basically I'm testing 3x plus 2y is greater than negative 6, and 3x minus 2y is greater than 6. So again, I would plug it in. Here I'm plugging in 0, 0, and here I'm plugging in 4 and 4. And as a result, I get the following answer. I get 8 is greater than negative 6, and negative 8 is greater than 6. Is 8 in fact greater than negative 6? Yes, that's true. Is negative 8 in fact greater than 6? That is not true. And so because it is not true for this solution set, or because it is not true for this inequality, and this is a solution set that's outside of the bounds, then I know that that answer choice is in fact going to be my answer, because that the inequality I'm looking for can only contain true statements that exist within my bounds. So within this shaded area that I have here. Okay. Another way I could go about solving that is if I were to graph it, I would actually see that the answer choice B, actually its graph looks like this. Oh, no. I don't like that because it just contained. Its graph actually looks like this. And so that's not what I'm looking for, and that's why C is my answer. So either way I can go about solving this. I can graph it or I can plug it in. But basically my steps here would be to 1, try a solution set within the bounds, within the shaded area. And if I'm not able to eliminate all the answers and just leave one, well, then the next thing I would do is I would take my 2 remaining answers and I would try a solution set outside the area, outside the shaded area. And if I get an answer that is true, then that will not be my answer. I'm looking for one that is false, because if it's false, well then obviously all its solutions have to be within that shaded area. Okay. Any questions? And I'll just go ahead and show you the right answer on the graphing calculator. And you'll see that it actually does in fact match it. So the right answer is 3x minus 2y is greater than 6. You'll see that that matches that blue part right there, right? Oops. That matches that blue part, where the other answer that we were looking at, oh, this is actually 2y. But it's still same thing. You'll notice this is our incorrect answer, the one I'm about to put in. 3x 3x plus 2y is greater than negative 6. And so you'll see that's a completely different graph than what the graph we're looking for. accidentally log out. Okay. Any questions?
No, ma'am.
No? Okay. All right. If there's no other questions, you guys may log off and work on your independent practice, and I will see you guys tomorrow. Bye, guys.
Bye, miss. Have a great day.
Bye, you too.